So, in the last class you remember what we did was to prove that if a linear programming problem is bounded below, then and I took a linear programming problem of a certain more relaxed kind and showed that if it is bounded below, it has a minimum, a minimizer exists. Now, what we were taking this part of the convex optimization course is on this special topic of linear programming, a special convex optimization problem, which I would like to call this little part of the course, a sub course, which is called the pleasures of linear programming, because possibly this is what one can call as real mathematics, beautiful results, beautiful algorithms, and at the same time beautiful applications and huge applications. Now, if I go back to what I wrote in the last class, meanwhile I took a little bit of, you might say, vacation, a little bit of holiday. So, like you might say I am coming back after the summer and talking to you, and so here I have written prove the above result for LP. Actually, the last result which I requested you to prove for LP means our LP, the standard form. So, it should be for, does not matter. So, I just did the correction with the blue one. So, here again I would now go over to the simplex method. So, simplex method. So, what I am going to do is to lay the foundations to this method. Simplex method was introduced, or rather developed by the famous operation researcher, or actually a mathematician, George B. Danzig in 1947. In fact, it is good to tell you how the name linear programming came, because once George Danzig was taking a walk with a very famous economist, T.C. Koopmans, and Koopmans asked him, George, what are you working on right now? He said that, okay, I am working on certain problems which has to do with minimizing linear functions subject to linear constraints or affine constraints, and these problems are coming out of applications for certain programs of the US Navy, certain strategical programs of the US Navy, in order to solve those issues. So, but I do not know what should I call it. Should I call it optimization with linear objectives and constraints? Koopman said, why do not you call it linear programming, and that is why the name linear programming as well as mathematical programming, which largely talks about maybe nonlinear convex optimization problems, came into vogue. Now, simplex method is usually taught in standard undergraduate classes using what is called a simplex tableau, a table, tableau or simplex tableau. So, it is a tricky way to solve the Gauss elimination process, and also at the same time do some bookkeeping to keep up the check on optimality. Now, let me tell you that I will not discuss the tableau. Our approach would have no tableau. Those who already have done some linear programming and possibly was in this course to talk about, know about something about convex programming, they can be rest assured that I will not bore them again with the tableau. So, you might be asking, and for those who have not, I would also refer to you a course by in the same NPTEL program, which talks about tableau methods, is a course completely on linear programming. So, why our approach would have no tableau? This Tableau-less approach was possibly pioneered in the book by Manfred Padberg, who is himself was a student of Danzig. So, he wrote a book called Linear Optimization and Extensions. It was published by Springer, I think way back in 1990 or 92, something like that, I guess 91. So, this book he promotes the idea of doing linear programming without the Tableau method. You might ask how that is possible for those who have already done some linear programming. First of all, what do you do in optimization when you run an algorithm? You take a start or a test point x naught, initial guess point, because you need to start the algorithm. So, you guess something, okay, is this the solution? You make a guess. So, there will be two options. You say yes, it is really the solution, then you stop the algorithm. And if you say no, it is not, then by some approach you move from x naught to x 1 such that the functional value, say if the function, my objective function f is f, the functional value at x 1 must be strictly less than f of x naught, provided that we are minimizing the function. So, you come from x naught to x 1 where this property is. So, you make a descent in terms of the functional value. So, this direction which you move from x naught to x 1 would be called direction of descent. Now, this is the basic fundamentals of an optimization algorithm. How you go from x naught to x 1 is the question which would interest us, because there are many ways to go through, and lot of research still goes on how to go from x naught to x 1 for various types of optimization problem. But when you look at the Tableau, the simplex method, you will see it does not tell me immediately, it is not apparent whether it is telling me to go from x naught to x 1. Yeah, it is telling you to go from x naught to x 1, because that is what any optimization algorithm would do, but just by looking at it, it is not possible to tell you whether it is going from x naught to x 1. But here we make a clear picture that we are going from x naught to x 1 and it will be done. So, a very important thing to keep in mind when you do linear programming is that any optimal solution is a basic feasible solution. Any optimal solution of the linear programming problem is a basic feasible solution. Any optimal solution is a basic feasible solution, or BFS. Now, you might ask me, okay, how do I accept your things? Those who already know convex optimization or just looking at this video for fun to see what is up there on the net. So, you would immediately realize that you can convert a linear programming problem into convex maximization problem, and then you know that it will be on the boundary, the solution, and not only in the boundary, it will be in one of the vertices if the thing is polyhedral. So, let me not get into those details, but I will prove this fact, but for the time being you consider this as a fact which is a true fact. So, we will prove it, proof later. So, what the simplex method will do? Simplex method will take a BFS and go from one other BFS to the next BFS, because every vertex of the convex polyhedra, which is the feasible set, that is, if you look at the convex polyhedra C or S, I guess C, I was marking as C or particular. If you look at this, this is a polyhedron and this has vertices. So, every vertex of the polyhedral C we know is a basic feasible solution, but then if the number of vertices are very large, which happens in most problems, you cannot keep on computing each and every vertex and then trying to enlist from in a ascending order. So, you know what is the minimum. So, this is a very time taking process and would be an NP hard process if they are large, this would be too large. So, if the number of vertices would be too large. So, what would we do? So, we have to find a clever way. The clever way is that if I have a BFS now which does not correspond to the solution, then I move to another BFS or another vertex in such a clever way such that in the new BFS, when I get the new BFS, the basic feasible solution or the optimal value corresponding to the or the objective function corresponding to that particular BFS would be strictly lower than that than the objective value for the previous BFS. So, I have made a descent. So, the simplex method does exactly the same thing. We will also now do the simplex method, but without the tableau. So, the tableau, what we do is a simplex method, and the simplex method, like any optimization method, goes from x 0 to x 1. But if you look at the tableau, it is not clear whether it is going from x 0 to x 1, because you get bogged down into a series of calculations which is same as the pivoting technique in Gaussian elimination, and you get bogged down with those calculations, and the real idea behind the simplex method goes off. And those who would read Manfred Padberg, a very fat tome, but if you read it, it is possibly one of the best mathematics books I have read. So, if you read Manfred Padberg, you would come across this fact that no software uses Tableau. Because Tableau, as you see, can be done for certain 6-7 variable problems, possibly with hand, but no software which are supposed to deal with a large amount of variables, a huge large linear programming problems, would really not deal with this. Now, the question would be, then if it is not dealing with this, then how does the software actually compute? How does the software do the simplex method? So, we will take the approach which will tell you how the software actually would run the simplex method. Our approach would based on Manfred Padberg. So, we are using Manfred Padberg's approach. There will be no Tableau, and that this approach I am giving is from the book. I am sure many of you would not have read it or even heard about this book, but a wonderful book, not only from the point of view of optimization, but also mathematically exciting. So, again we now go back, start our foundations of the simplex method. So, our problem, again to recall for those who would not remember what has been done earlier, is to really minimize this linear function such that a x equal to b and x greater than 0. So, in his approach, Manfred takes certain assumption which are quite natural. So, the assumption is that A does not have a 0 column, so you see if it has a 0 column. So, there is basically one particular variable does not come in the feasible set. So, that variable can take any value that you can give. So, you can really fix up the other variables which are actually appearing and then put whatever value you want for that variable. So, A if has a 0 column, that 0 column would not interest us. So, for a computational point of view, we do not want an A which has a 0 column. If it does not have a 0 column, it is true. If it is a 0 column, we really have to get rid of that and then try to do the thing. So, the first assumption is A does not have a 0 column, and second, which is the standard assumption, that it is a full row rank. So, rank of A is M, where M, as you know, is number of rows. Now, let me state you a curious fact. What about it? Do you have any assumption on B? The answer is interesting, because if B is equal to 0, then either x equal to 0 is an optimal for the linear programming problem, or LP is not bounded below. So, here there is a cute little proof in Manfred Padberg which I want to reproduce. So, if B is equal to 0, then x is equal to 0 is an obvious feasible point now. If x bar be an optimal solution, which we assume it exists, then C transpose x bar or C of x bar is greater than equal to C transpose x. Sorry, I made a mistake. C transpose x bar, which is a solution, is less than equal to C transpose x for all x feasible. Now, x equal to 0 is feasible. So, C transpose x bar is less than or equal to 0. What we have to show that C transpose x bar less than equal to 0 is strictly less than equal to 0 is not possible. We must have C transpose x bar equal to 0. If C transpose x bar is strictly less than 0, we will show that the problem would be unbounded below. So, if C transpose x bar is equal to 0, then of course, x equal to 0 is a solution, not the only solution, but possibly is, but is a solution. So, let there exists a feasible x such that C transpose x is strictly less than 0. Now, consider any lambda greater than equal to 0, maybe greater than 0, does not matter. So, A of lambda x is lambda A x is equal to lambda of B, and B is equal to 0. So, lambda into 0 is equal to 0. So, this would imply that lambda x is feasible for all lambda greater than 0. Therefore, C transpose lambda x, obviously, because if I take lambda greater than equal to say for lambda greater than 0, C transpose lambda x is also strictly less than 0. So, which means lambda transpose C x is strictly less than 0. So, as lambda tends to plus infinity, because C transpose C, this C x is strictly less than 0, it implies to not go down, it goes up to plus infinity. Lambda goes up to plus infinity, it is clear that this one, that is C transpose lambda x, is immediately rushing to minus infinity. So, which proves that this is unbounded below if C transpose x, there is a feasible x as the C transpose x is less than equal to 0. So, when B is equal to 0, C transpose x bar cannot be strictly less than 0, but it has to be equal to 0. So, if it is equal to 0, which means C transpose 0 is also equal to 0, which is the minimum. So, 0 is the minimum value, and so which would imply that x equal to 0. So, 0 is the minimum value, and thus x equal to 0 is a solution. So, in most cases you will not see in the real problems that B is equal to 0, B is hardly equal to 0. So, to begin with, let us fix up some notations. Notations are very important as we go along. So, we will fix up some notations. Let us consider J to be the set of indexes marking the rows of the matrix A, M cross N matrix of full rank, and I x for a given x, I should write I of x, but I am just writing it like this to keep it separate from the active index set that we have already spoken about while studying Kuhn-Tucker condition, keeping it slightly separate than the active index set, because here it is not exactly the active index set, it is essentially some sort of inactive index set which would be important for some time. And J set minus I x would consist of all j in J such that x of j is equal to 0. So, for a fixed x we are just collecting indexes, these are index sets. So, if x is feasible to LP, then x satisfies that is, we can write down the fact that Ax is equal to b and x greater than equal to 0 as follows: Ax equal to b and x of j is equal to 0 for all j which is in J, but not in Ix. So, we can write the matrix, it is similar to the splitting that we did for basic and non-basic, it is quite similar, but if you write the matrix now of the equation, we can write it in this way. So, Ax equal to b can be reformulated So, consider Aix, that is, this is the matrix whose rows consists of those rows. So, your column is same, it consists of those rows which belong to Ix, J is 1 to m. So, it consists of those rows which belong to Ix. So, we can write down this form in this partition form. We will write down what everything means. So, A has m rows and J has m rows. What is Aix? So, how many columns this matrix has? We will all fix it up right now. We are just writing it, you just hold on with me for some time and I will just. Now, you will see what is this Kx. So, this is something we need to know. So, let us write down Kx is cardinality of Ix. So, I am cardinality of this set. So, this is the cardinality of Ix, right. So, corresponding to the cardinality of Ix, I have split the A. Suppose Ix is say this one, sorry not M, I am making a mistake, this should be N, please take a note. So, you have this whole xj vector x1 x2 dot 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 n xn in Rn, and now you are splitting it up into two parts. First part is you are taking some indexes for which xj is strictly greater than 0, some index which is xj is equal to 0, because xj must be greater than or equal to 0, each of the xj's. So, we take those indexes for which those particular columns for which xj is strictly greater than 0, we assume that they are in the first part. So, we take those separate and remaining n minus kx, right. So, n is obviously the cardinality of j, which is the counting of the number of components, because x is in Rn. So, remaining j minus Ix is the case where xj equal to 0. So, you split the n columns into these belongings. some columns for corresponding to which xj is strictly greater than 0, some column for which xj is equal to 0. So, now it is not that the first ix columns or first kx columns are having xj greater than equal to 0, it could be otherwise, but just by applying a permutation matrix from both sides you can make this arrangement. So, finally, what we get is a similar matrix of this type. So, from the point of view of solution, this matrix and the one, if you had not kept aix all on one side, but something in the some of them in the middle, then also it would give me the same solution. So, aix is of the order m cross kx. So, a j minus ix is of the order of m cross n minus kx. So, x ix, if you are multiplying, if you take this a, so there are ix rows. So, you can multiply with these ix columns. So, you multiply with these ix rows here. So, these are strictly bigger than 0. The remaining part j minus ix, all of them xj's are equal to 0. So, you can see that what you finally get is exactly, and here this is 0 and this is the identity matrix of xj greater than xj equal to 0. So, if you look at this, you will exactly get back this. So, your homework would be to check that this corresponds to the solution of corresponds to this equation. So, homework is to check this and this. Okay. Now, once we know this notation, we have the following, that the rank of aix, a j minus ix, 0 I n minus kx, this thing is can be is same as rank of why? Because n minus kx corresponds to linearly independent columns, and only the linearly independent columns in this matrix would now add up to give you the rank of A. So, we have split it up like this. So, the above matrix equation means the one which is in the previous page, gives us a unique solution if column rank equals row is equal to the number of, if the column rank or row rank, or if the row rank is equal to the number of columns. So, it is a full rank, that is if the matrix is of full rank. That is rank of aix is rank of this matrix plus n minus kx is equal to n. So, there is a unique solution if and only if rank of, if you just do certain simple algebra, equal to the cardinality of ix, or cardinality of ix is also denoted like this, which you know. So, this is something we can immediately come across. So, since rank of A, so the A is basically partitioned into these two parts. So, rank of A is m, m is full rank. So, rank of aix, sorry, rank of aix would also be m, of course, would look like to be m, but that is not the case. So, rank of aix, which is Ix, that is if it has a full solution, rank of Aix, if you look at it, rank of Aix, here I do not have all the n columns, I have the number of linearly independent columns in this matrix has to be less than m, because rank of A is m. So, in the matrix A there are only m linearly independent columns. So, if I take all those rows and only few columns, then what I am getting is rank of Aix must be less than or equal to the total given rank m. So, now we will have certain, in order to study the simplex method, we will make certain notations, which is the Manfred part back style of notation. So, we will maintain that sort of notation in our study of the simplex method. So, we know what we call BFS by partitioning, B, N and N, all those things. Here also we are doing the same thing, but partitioning, but giving a different name to it, different symbols to it. We will say X is called a BFS if rank Aix so your solution would be a BFS if this is exactly your B part, which will be a square matrix. So, rank of Aix would be exactly equal to Ix if m is more than m. So, m should be here its full rank. So, rank of Aix should be is equal to Ix. So, that is what we will call a BFS, in the sense that if this rank Aix is its full rank and the number of columns in this is also m. So, this is exactly would be your B, that we have seen that B and N separation in the earlier lectures, that is exactly this story, that B story is written like this. So, if this rank of Aix is m, which is rank of Aix is Ix and which is m, then we call it a BFS. So, what I want the rank of Aix should be equal to Ix. So, rank of Aix is equal to Ix, then we have a unique solution to this problem. So, there is a unique solution to this linear equation, it has a unique solution. So, then rank of Aix would be Ix, and but if this Ix equal to m, then this is your basis matrix, Aix becomes basis matrix. Aix is the starting basis, or just basis is the basis matrix. Okay. So, what we have done? We have taken a J, which is a solid, what we have done, let us recollect. It might not be so easy for everyone. What we have done so far, is that if X is a feasible solution, then X satisfies these equations, right, and we are telling that if X is the only solution of this equation, right, that is having these particularities, that X is equal to 0 for this number of for all these J's, then Ax equal to B and X greater than is equal to 0, or rather I would say this fact, this expression can be reformulated, this can be reformulated as, this whole expression can be now reformulated as follows, means writing this is same as writing this, and which I say it is of this form, and if this there is only one X which has those properties with the Xj's, that is okay, I have this is the only possible X for which X is partitioned like this and is solving the system, then rank of Aix must be equal to the cardinality of Ix, and if the cardinality of Ix is also equal to m, so then X is the only solution of that particular system of equation which we just show, and then that solution is called a BFS if its rank, that is cardinality of Ix, is also m. So, it is slightly different way of telling you the same thing, that if this happens, then this is your actual B. So, X is called a degenerate BFS is rank of AIX is equal to IX is equal to M. Maybe I should write it more clearly. So, any M cross M submatrix B of A is called a basis matrix. And X is called a BFS, a basis is called feasible, sorry, X is a BFS, it is already given. So, B is called feasible, because you have seen that when you compute the basic feasible solution, there is two parts, XB and XN. XN is 0 for the basic feasible solution, and XB is nothing but B inverse B of some such a submatrix, such a basis matrix. So, B is called feasible. So, if X it has to be a BFS, then B inverse B has to be 0, then B inverse B must be, sorry, not have to be 0, has to be greater than or equal to 0. So, these are the basic notations that we require. So, once we know the notations, we need to talk about some very fundamental stuff about linear programming. So, the main result that we are going to prove, that if there exists X element of C, then there exists a BFS X bar element of C. So, if X is feasible, there is a feasible solution, that it is a polyhedron, then there is a BFS, and if there is an optimal solution, there is an optimal BFS also, basic feasible solution. This is the most important result that tells you that okay, and every BFS we have proved to be a vertex. So, there is a one-to-one correspondence. So, every basic optimal basic feasible solution lies at the vertex. So, we have to jump from one vertex to the other, but do it in a clever way, so that the objective value decreases strictly, and that is exactly what is the simplex method going to do, and the clever way is the technique, simplex technique. But it is somewhat important that we need to not only know these results, but from mathematical point of view we need to work down through the proofs of this result, because this in the proof of this result the inherent technique of simplex method is hiding in the proof of this result, and then we will write, when we will write down the simplex method, you will soon see what I am telling is so correct. So, tomorrow we will concentrate on proving two results. The first result is, if X is a basic feasible solution, then X has at most M positive components, because rank of A is M, and the submatrix which we defined is AIX. This can be extended to a feasible basis by adjoining AIX with some more columns from the remaining part. If this is not M number of columns, I can take something from this and make it into a basis matrix, and not only a basis matrix, it can be made into a feasible basis matrix. And then once that is done, we have to prove the very fundamental theorem of linear programming. If there exists an X element of C, then there exists a BFS. If there is an optimal solution to LP, then there is an optimal basic feasible solution. This is exactly what we will study in tomorrow's class.